So we're talking about solutions. We've been talking about solutions. When you dissolve ionic compounds, which is what we mean by salts, when you dissolve them, they form ions, and the ions might be acidic or basic, depending on where they came from or where they may have originated from. And so we're going to be interested in trying to figure out, first qualitatively, whether or not a salt solution will be acidic or basic, depending on the ions that are in there. Okay, so how you do this? First, you figure out which ion, where each ion in the salt comes from. So, for example, KCN, potassium cyanide. The two ions that are produced are K plus and CN minus. K plus would come from a strong base, like KOH. CN minus comes from a weak acid, like HCN. Okay? Well, once I know sort of where they come from, I can determine what quality that gives each ion. If K plus came from a strong base, it must be a very weak conjugate acid. And if CN minus came from a weak acid, then it must be a pretty strong conjugate base. So we can then compare the two ions and determine the overall acidity or basicity of the solution. This solution, KCN, should be fairly basic because it has a strong conjugate base but a very weak conjugate acid. So it should be overall pretty basic. Okay? Cations in general, you'll have weak conjugate acids if they come from strong bases like 1 or 2 plus ions, the alkali metal ions, alkaline earth metal ions. Those come from strong bases. Okay? Strong conjugate acids will come from weak bases, so things like the ammonium ion or a C5H5NH, which is called an anilonium ion. Very strange. Or C5H5NH. NH4 plus comes from NH3. C5H5NH plus comes from C5H5N. Okay. Highly charged metal ions like aluminum or iron 3 are also strong conjugate acids. Okay, so they contribute to the acidity of a solution. For anions, weak conjugate bases will come from strong acids again, so chloride ions or hydrogen sulfate ions, because they come from strong acids. Strong conjugate bases will result from weak acids. Okay, so the bicarbonate ion, for example, and nitrite ion come from weak acids, so they would be strong conjugate bases. So sometimes it'll be difficult because you'll have one ion that is very acidic and the other one is basic. How do you tell whether the overall solution is acidic or basic? Compare the K values. Okay. General rule of thumb is if Ka is greater than Kb, then the solution is acidic, and vice versa. Okay. The interesting property of Ka and Kb that's kind of helpful to know sometimes is when you multiply Ka times Kb, you always get Kw for any weak acid and its conjugate base. Okay. So sometimes you can use this relationship. So let's practice a little bit. Tell me which of the following will be acidic, basic, or neutral. NH4Br. What do you think? Well, NH4 plus is a strong conjugate acid because it came from a weak base. Br minus is a weak base, weak conjugate base because it came from a strong acid. So overall, this would be an acidic solution. What about FeCl3? Fe plus 3 is a strong conjugate acid. Highly charged metal ions are strong conjugate acids. Cl minus is a weak conjugate base because it comes from a strong acid, HCl. So this should be an acidic solution overall. How about Na2CO3? All right, well, Na plus is a weak conjugate acid because it comes from a strong base. CO3 2 minus is a strong conjugate base because it comes from a weak acid. So this should be a basic solution. KClO4. Potassium perchlorate. K plus is a weak conjugate acid. ClO4 minus is a weak conjugate base. So both are weak. What do we think? If both are weak, we say it's neutral. K plus doesn't generally act as an acid. It won't donate a proton. It won't produce OH minus. And ClO4 minus is a very weak base. It doesn't accept protons. So if you have both weak, we say it's neutral. How about NaHC2O4? Na plus is weak. HC2O4 is a strong conjugate base because it comes from H2C2O4, which is called, say it with me, oxalic acid. So overall, this will be a basic solution. Now, what if we're going to find the pH of a salt solution? Well, we have to figure out what it's going to look like, and then we kind of have to do some calculations that are very familiar, that we've done them before. Okay, KF, 0.20 molar solution. KF splits up into K plus and F minus, which will affect the pH of the solution. Well, K plus is a weak conjugate acid. F minus is a strong conjugate base. We can ignore the K plus and really concentrate just on the F minus. Okay, F minus will react with water to produce HF and OH minus. Initial concentration is 0.20 molar, nothing for HF or OH minus initially. Concentration of the F minus will go down a little bit, HF and OH minus will go up by the same amount. We have our usual ice table. We can put this into our Kb expression. Kb for F minus is 7.2 times 10 to the minus 4. We can make the approximation. We can check the approximation. It's valid. So we have our value for X. X in our ice table is hydroxide ions. So we can find the H plus concentration. Again, divide Kw by the OH minus concentration. You'll have that. Take the negative log. You get a pH of 12.58. So here's a summary table from your book. Types of salts, some examples, and whether or not it will be acidic, basic, or neutral. Sometimes you have to check your Ka and Kb values to figure out what's going on. So one of the things that you should be able to explain is what leads certain things to be acidic and certain things to not be acidic, which means you need a knowledge of the structure of molecules in this case. In general, it has to do with how easy it is to remove a hydrogen ion from a molecule. So if a hydrogen is attached to a molecule by a weak bond or a very, very polar bond, then it's going to be easy to break that bond unevenly and produce that H+. Likewise, though, if the bond between the hydrogen and the rest of the molecule is strong or nonpolar, then it's going to be much harder to break it, and it's not likely to become acidic. Some things that come into play: the more polar the bond between the hydrogen and the molecule is, the stronger the acid will be. So if the bond breaks very easily, then those molecules are going to replace a lot of H+ into solution. If it's less polar, it might take more energy to break, and therefore not as many molecules will do it. If the atoms around that bond are more electronegative, they're going to pull electrons towards themselves. They're going to weaken that bond, and that means it'll be a stronger acid. If the hydrogen is attached to a halogen, the more electronegative the halogen, the more easily that hydrogen ion will come off. Okay, and the stronger the acid will be. With the exception of HF, fluoride has something else going on because of its very small size that makes it a weak acid. The size of atoms involved. The larger the atom, the weaker the bond, the stronger the acid. Okay, so for example, HF, HCl, HBr, HI. Okay, that's one of the reasons that fluoride, HF, is a weak acid. Even though the fluorine is very electronegative, it's so small that it's actually a fairly strong bond to that hydrogen, which makes it a weak acid. So that's essentially why. Okay, HI is a very weak bond because I is very large, and so HI is a strong acid. If you have oxy acids, then the number of oxygens in the oxy acid will affect how acidic it is. The higher the number of oxygens, the more polar the bond is, the stronger that acid is. For example, HOCl versus HClO2 versus HClO3 versus HClO4. You have one oxygen in HOCl, hypochlorous acid. You don't have a very strong acid, but if you go up to 4 oxygens, that bond to the hydrogen is very weak, and perchloric acid is a strong acid. So for example, which is stronger of an acid, and then explain. Okay, HNO2 or HClO2? Well, both have 2 oxygens, but the central atom is the important piece here. Chlorine, is more electronegative than N. So since it's more electronegative, it's going to be pulling electrons towards itself, and it'll weaken that bond to the hydrogen. How about HNO3 or HNO2? Well, HNO3 has more oxygens than HNO2, so that's going to be a stronger acid. How about CCl3COOH, which is called trichloroacetic acid, or CH3COOH, which is just acetic acid, which is a stronger acid there? Well, trichloroacetic acid has these very electronegative chlorines on that carbon, and that pulls electrons away from the ionizable hydrogen. So you can evaluate qualitatively acid strength simply by looking at electronegativities, the amount of oxygens present, how weak the bond is to the hydrogen.